So we talked on Monday about some of the basics and the idea of a count and a name, and we're going to continue with that a little bit today. Don't think of it as basic math. Think of it as number theory. We're going to be looking at some of what is going on behind the way we do the operations with numbers. And again, the purpose of that is so that when we get to our algebraic numbers, the process is the same. Notes, as I mentioned, scheduling. I'll bring that up here. So I do have the schedules from each school, and I've got stuff put on the a grid trying to figure out what we're going to do. It looks like we're pretty clear for the next couple of weeks. So we'll be able to finish up Unit 1 and have Test 1 on February 8th. It's actually after February 8th that we start having different days off at each school. So once we get closer to that time, we'll discuss how we're going to handle that. And we do have a stretch there where each school has a different day off. So what we'll do is we'll probably do a rotation where we do the same lecture twice or something like that so that people aren't missing out. So anyway, continuing on with our why behind our basic math. We're going to look today at another one of those very simple concepts that has huge consequences when it comes to some basic operations. Concept is the concept of value. And so we all know the idea of put it here.
Sure.
Are you guys able to hear me in Boston?
Yeah.
Okay. So our place values, of course, we start off with tens, and the hundreds. Those are our only three place values, and they continue. Tens, tens, hundreds, and they keep repeating. This was our base group. Have a thousands group, and millions. Not gonna insult your intelligence about your intelligence and stuff like that. But these place values are very tying in. We're getting a horrible echo. I'm going to go ahead and mute you guys and mute you guys and cancel out the echo. So if you need to say anything, you have to give me a wave. All right, that seems to have fixed it. Okay, perfect. So anyway, these place values, the purpose they have or how they tie into what we talked about Monday and into the bigger picture of things is when we look at a number like 374. We're used to looking at that as being the full number, but it really isn't. That's an abbreviation. The full form of that number looks like this: 300s and 7 tens and 4 ones. And when we see it like that, we realize that every digit is a count and a name. This isn't just a 7, it's 7 tens. And so now when we go to add numbers, if I try to add 523 to that, if I put that out in that full form, or what some schools call expanded form, that would be 500s, 2 tens, and 3 ones. And if you recall from Monday, when we add or subtract numbers, we can only combine things with the same name. And that comes right down to the individual digit. I can only combine ones with other ones, and tens with other tens, and hundreds with other hundreds. This is why we were told that you have to line up the columns when you add. So once they're lined up, we go ahead and add. 3 and 5 make 800s. 7 and 2 make 9 tens, and 4 and 3 make 7 ones, giving us 897. Now, if you're paying attention there, you might have noticed I did something a little unusual when I added those numbers. I started at the right and started at the left and I worked my way to the right, just like reading a book. But we're used to going the other way, starting at the end of the number, at the right side, and working our way backwards to the left. When we add numbers, why do we do that? Yes, in case we have to carry. We might have 574 plus 298. We start at the end of the number because we run into this. 4 plus 8 makes 12. We can't have two digits in the same place value, so we keep the 2 and carry the 1. 1 and 7 is 8, plus 9 is 17. Again, we keep the 7 and we carry the 1. 1 and 5 is 6, plus 2 is 8. We get 878. Now, this process of carrying is actually just one way of adding numbers. It's been the most popular over the last couple hundred years, but there are a lot of other ways that we can add numbers and get the same result. One of them would look like this. 574 plus 298. They start at the beginning of the number. 5 plus 2 is 7. 7 plus 9 is 16, so 6, drop the 1. 4 plus 8 is 12. 2, drop the 1. 872. Now, I'm not trying to get to change the way you add numbers by any means. I show you this only because there's a myth in math that there's only one correct process to do things. That's not true. There's only one correct answer, but there are several processes you could go through to get to that answer. So I show you this to make that point of if you have a process that's different from what I do, it's not necessarily wrong. If you're not sure if it's going to work every time, let me know and I'd be happy to take a look at it and see if it's something that's going to work each time you need to use it. Subtraction. Might have 875 minus 263. Now, I could write this out in that full form, but I think you guys get the point that we can only combine digits that have the same place value. So we line up those columns. And again, once they're lined up, we go ahead and subtract. 8 minus 2 is 6. 7 minus 6 is 1. 5 minus 3 is 2. Now again, I did that backwards. I went from the left to the right. We're used to going the other direction when we subtract in case we have to, for subtraction, it'd be borrowing. So we might have 735 minus 296. We start at the end of the number and work backwards because we hit this. 5 minus 6 can't be done, so we're going to borrow from the 3. That's a 2. This now is a 15. 15 minus 6 is 9. 2 minus 9 can't be done. We borrow from the 7. That's a 6. This is 12. 12 minus 9 is 3. And 6 minus 2 is 4. Now again, that process of borrowing is only one of the methods that could be used. Different method, another method, would look like this. 7 minus 2 is 5. 3 minus 9 can't be done, so we actually take from the 5. That's a 4. This is now 13. 13 minus 9 is 4. 5 minus 6 can't be done, so we take from the 4 to make it a 3. It's a 15. 15 minus 6 is 9. We get the same answer, it just takes a little bit more room and maybe a little bit more time. Again, the point is not to change how you subtract numbers, but to, again, demonstrate that there are alternative methods for doing a lot of these calculations. For multiplication, now we might have 32 times 21. Now this one I am going to write out in that long form or full form. 3 tens, 2 ones. This will be 2 tens and 1 1. Now if you remember from Monday, when we multiply or divide, we do not need the same name. So that means that these 3 tens can not only be combined with these 2 tens, but they can also be combined with the 1 1. In fact, every digit from one number can be combined with every digit from the other number. And that's really what the process of long multiplication is. That's all it is an organized method of making sure every digit from one number is combined with every digit from the other number. And the most common method that we've learned is put them, again, vertical like this. Start with the last digit of the bottom number and start combining it with the top number, starting with the last digit of the top number. 1, 1 times 2 ones. Well, we combine counts. 1 times 2 is 2. And we also combine the names. We combine the place values. Up here, when we added or subtract, we kept the same names. So we just brought down the place values, ones, tens, and hundreds. When we multiply, remember, we have to also combine the names. Ones times ones is just ones. That's a positive 2, so I'll put a plus there. We combine with the next digit up top. 1, 1 times 3 tens. Again, combining counts. 1 times 3 is 3. And then combining names. Ones times tens is tens. When we move over to this next digit, we've always been taught that we have to leave a space down here or put in a 0. Well, the reason for that will be apparent here in this step. We have 2 tens times 2 ones. We combine the counts. 2 times 2 is 4. Tens times ones is tens. We put in that 0 there just to make sure our place values stayed lined up. Then we move over here. 3 tens times 2 tens. 3 times 2 is 6. Tens times tens is hundreds. And then we just add them up. 2 ones, 7 tens, 6 hundreds to get 672. Now again, this is the way we're used to seeing it, but there are other ways of doing it. We could have our 3 tens and 2 ones times 2 tens and 1 1. For those of you that have taken algebra, you've seen this method done with algebraic numbers or polynomials. Basically, it's the FOIL method. 3 tens times 2 tens. 3 times 2 is 6. Tens times tens is hundreds. 3 tens times 1 1. 3 times 1 is 3. Tens times 1 is tens. 2 ones times 2 tens. 2 times 2 is 4. Ones times tens is tens. And 2 ones times 1 1. 2 times 1 is 2. Ones times 1 is ones. And we add those up, 672. Just like we would do with our algebraic numbers and doing the FOIL method with polynomials. And again, there are other methods I could use. The purpose is just to show you that there isn't just one single way of doing it. Before we move on to division, I want to mention a little bit about the mechanics of multiplication. We're going to do, as the day goes on, we're going to do some more with the mechanics of addition as well. But something like 5 times 3. If we go back to first grade or so, before we memorized our multiplication tables and we just knew 5 times 3 was 15, how did we figure that out? Oh yeah, we did 5 plus 5 plus 5. We did repeated addition. 5 plus 5 plus 5 is 15. Well, we said that division follows the same rules as multiplication. So if multiplication is repeated addition, division should be repeated subtraction. Let's try it. 24 divided by 8. Let's subtract 8 from 24. That gives us 16. And let's repeatedly keep subtracting 8. 16 minus 8 is 8. 8 minus 8 is 0. Well, 24 divided by 8 equals 3 because I can subtract 8 from 24 1, 2, 3 times before I hit 0. So division can be thought of as repeated subtraction. In fact, that's where our remainders come from. I have like 32 divided by 6. Well, 32 minus 6 is 26. That's once. 26 minus 6 is 20. That's twice. 20 minus 6 is 14. That's 3 times. 14 minus 6 is 8. That's 4 times. 8 minus 6 is 2. That's 5 times. And I can't take out another 6. So 32 divided by 6 is 5 with a remainder of 2 because there was 2 left over after we had subtracted 6 the 5 times. Well, now let's look at how does that tie into bigger numbers. and eventually a process of long division. The process of long division is the one operation that's really been abbreviated and shortcutted to the point where you don't even recognize it. But anyway, if I had something like 84 divided by 2, I'm really not about to start subtracting 2 from the 84. I don't want to put in that kind of time. But I can start taking large chunks of 2 away from the 84. That's where our long division process comes in. And to figure out how big of a chunk, we look at this first digit of the number being divided and its place value. That's in the tens place. So we do 10 times 2 is 20. I can subtract 20 from the 84. In fact, I can do it multiple times. I can do it 4 times. 20 times 4 is 80. I subtract the 20, I'm left with 4. Well, what I really subtracted there was I subtracted a bundle of 10 2s, and I did it 4 times. So 10 times 4 is 40. Well, now I'm down to the next place values, the 1s. 1 times 2 is just 2. I can take that out of what's left twice. 2 times 2 would be 4, leaving me with nothing. So up here again, I took a bundle of 1, 2, and I did it twice. 1 times 2 is 2. 40 plus 2 is 42. 84 divided by 2 is 42. Now again, that's way longer than the version we've been taught. But it's actually all the steps. Most of these other steps here, we've just been taught to do those in our head, basically, and leave those off. Or we've abbreviated the process so that we didn't have to do those longer steps. But when we do the full form of long division, let's take something like 68,458 divided by 21. Now again, I'm not about to start subtracting 21 from 68,000. We don't have that kind of free time. But we can look at subtracting big chunks of 21. And we start with the place value of the first digit of the number we're dividing. That's in the 10,000s place. 10,000 times 21 is 210,000. That's too big. We cannot subtract that. So we'll move to the next place value, the thousands place. 1,000 times 21 is 21,000. We can subtract that. In fact, we can subtract it 3 times. 21,000 times 3 is 63,000. Subtract that, and we have 5,458 left. But what we really subtracted there is we took a bundle of 1,000 21s. And we did it 3 times. 1,000 times 3, 3,000. That 63,000 that we subtracted was really 3,000 21s. Now we move to the next place value, the hundreds place. 100 times 21 is 2,100. Now again, I can subtract that from what's left. I can do it twice. 2,100 times 2, 4,200. I subtract, I'm left with 8, 5, 2, and 1. 1,258. Now again, what I just subtracted, I did a bundle of 121s, and I subtracted it twice. 100 times 2 is 200. That 4,200 that I subtracted is really 221s. Next place value, tens. 10 times 21 is 210. I can subtract that from what's left. In fact, I can do it. 6 won't quite go. Well, we can do it 5 times. 1,050. Subtract 8, 0, and 2. 208. So what I really subtracted there again was 10 21s, and I did it 5 times. 10 times 5 is 50. That 1,050 that I subtracted was really 50 21s. And of course, now I'm down to just the ones place. 1 times 21 is 21. I can take that away from what's left 5 times again. 21, oops, not 5 times, 9 times. 21 times 9 is 189, which will leave us with 19. Again, we just subtracted a bundle of only 121 and we did it 9 times. 1 times 9 was 9 more 21s. So this is 3,259. And we had that remainder of 19. So 68,458 divided by 21 is 3,259 with a remainder of 19. Now you're probably looking at that thinking, that looks nothing like what I was taught for long division. And it doesn't look much like it, but it's the exact process. Just what we were taught left out a lot of the steps. Take a look. So what we were taught to do is you look at the first digit, 6. Does 21 go into 6? No, it doesn't. So we leave that blank and we move to the next digit. That's exactly what we did here. That was too big, so we moved to the next place value. 21 goes into 68? Yeah, 3 times. 3 times 21 is 63, and we subtract. That's exactly what we did here. We just left off all zeros. Bring down the next digit, the 4. 21 goes into 54 twice. 2 times 21 is 42. Subtract, there's 12. Again, that's exactly what we did here. We just left off the zeros. And so this whole process continues exactly like that. Bring down the next digit, 5. 21 goes in there 5 times. 5 times 21 is 105. Leave us with 20. Again, just left off zeros. There and here. So anyway, bring down that last digit, the 8. That goes in there 9 times, which is the 189. So leave us with the remainder of 19. So what we were taught is this whole process here. We just left out a lot. We skipped a lot of steps. We didn't write them out, or we did them in our head by only looking at certain digits instead of the whole number. But all this really is, this whole process of long division that we were taught, is just this organized method of doing repeated subtraction. When we look at algebraic numbers in a couple of weeks, we'll see when we do division with the algebraic numbers, it actually fits this longer process. So I show you that, again, not to make you do it that way, but so that when we get to some of those more advanced processes, you can see they're the same process. We're just not able to leave out some of those steps like we could with whole numbers. So next, we want to look at this process of mechanically combining the counts. At this point, we've assumed that you could combine the numbers, but let's look at how it's actually done. And to do that, we first need to look at how do we represent an amount, representing a count. And the most useful way that we can do that is on a number line. And we do it with a tool called a vector. Now, a vector is a real fancy name for a pretty simple concept. If I wanted to put a vector for the number 6 on my number line, I'd start at 0, and I'd make an arrow that goes to 6 like that. This vector has 2 properties. Property number 1 is its direction. It's either positive or negative. The 6 is going in the positive direction. The second property it has is something called its absolute value. Its absolute value is just its length. This vector here is 6 units long. It has an absolute value of 6. If I put a vector up here For negative 6, it would look like this. Notice it's the same length as the vector for 6. They have the same absolute value. It's just a different direction. So now if I go to add numbers, like five plus 3. This process of addition, the addition symbol, is telling us to combine vectors. So I start by putting the 5 up there. 5 would look like this, going from 0 to 5. And I put the 3 on there. 3 goes from 0 to 3. And so to combine those vectors, I can either take the 3 and copy it and move it to the end of the 5. Or I can take the 5 and copy it and move it to the end of the 3. Either way, I end up with one longer vector, and we can see it ends up at 8. 5 plus 3 is 8. We already knew that. We didn't need the vectors to tell us that. But when we throw in negative numbers, if I have 6 plus a negative 4, now I have my vector for 6. It's like this, 0 to 6. And my vector for negative 4, 0 to negative 4. And to combine those, I'll copy one. I'll just copy the negative 4 here. The 6. And I can see that puts me back at 2. 6 plus negative 4 is 2. So the vectors and their direction put us at the correct spot on the number line that gives us the answer. Now, I don't expect you to draw out number lines every time you work with integers. I certainly don't do it. But I do keep that picture in my mind as I'm working with them. For example, if I have 42 plus a negative 58, what I am picturing is this. I start at 0. Positive 42 goes in that direction. Negative 58 goes the other direction. It goes back this way. And 58 is longer than 42, so I go past the 0. So this picture shows me two things. One, I'm on the negative side of 0, so my answer is negative. The second thing it shows me is I look at my vectors. The vectors are going in opposite directions. Since they are going in opposite directions, the absolute value of my answer is the difference of their absolute values. So what that means is I take the bigger one, the 58, and minus the shorter one of 42, that gives me 16. So this is a negative 16 is that solution. That's how far we went past 0 into the negative side. Or we might have a negative 36 plus 41. Same thing. Here's 0. Negative 36 goes this way. 41 is positive. It goes the opposite direction. And 41 is longer than 36 again. So we pass 0 and we're in the positive side. So I know that my answer is positive. Once again, the vectors go in different directions. So the resulting length, or absolute value, is the difference of their lengths. 41 minus 36 is 5. It's a positive 5. I might have a negative 27 plus a negative 18. 0. Negative 27 goes that way. Negative 18 goes in the same direction. So this one's definitely negative. We're definitely on the negative side of 0. And the vectors go in the same direction. So since they go in the same direction, we just add their absolute values. 27 plus 18 is 45. So this answer is negative 45. So this picture gives us two things. It tells us which side of 0 we're on. Are we on the positive side or the negative side of 0? And the second thing it tells us is, do we add the values to get a longer vector, or do we subtract the values to get a difference vector? Well, subtraction, again, we know it is one of our simpler operations, but when we throw in the integers, the negative numbers, it is probably the most difficult operation. Let's start out with a basic one with positive numbers, 8 minus 3. If I were to ask you to draw out a vector picture for 8 minus 3, most people would draw out pretty much the same picture. Positive 8, negative 3, we end up at 5. 8 minus 3 equals 5. But as you look at this picture over here, you realize that this vector here is just the vector for negative 3. And that picture is the same picture as if we had 8 plus a negative 3. And there's a good reason why it's the same picture. It's because they're the same problem. We mentioned on Monday that subtraction is not an operation in itself. It's part of addition. Addition's going forward, subtraction's going in reverse. Well, here we see that the symbol for subtraction is actually telling us to do a form of addition. First of all, that symbol acts on the number that comes after it. So the 8 is not affected by that symbol. But the subtraction symbol means add the opposite of this number. So it means add what is the opposite of positive 3? That's negative 3. So you can see 8 minus 3 is the same as 8 plus a negative 3. Now, since 8 and 3 were positive, there's no need to change it. We know how to subtract. 8 minus 3 is 5. That's simple. No use making it more difficult by changing it to negatives. But where this comes into play is if we have like a negative 42 minus 23. That can be confusing to think of, but if we change it to that adding the opposite, remember the negative 42 doesn't change. The subtraction operates on the 23. So we change this to adding. The opposite of 23 is a negative 23. So our vector diagram, you have 0, negative 42, and negative 23. This is definitely in the negative direction, and we are adding the absolute values because the vectors go in the same direction. 42 plus 23 gives us 65. So our answer there is a negative 65. The one that really baffles people is this one. 18 minus a negative 24. Well, again, the 18 is not affected. That just stays 18. Subtraction operates on the number coming after it. So instead of subtracting, we're going to add. The opposite of negative 24 is a positive 24. That's just 18 plus 24, which is 42. Or we can run into negative 27 minus a negative 15. So same thing, the negative 27 does not change. Subtraction operates on the number coming after it. So we're going to add. The opposite of negative 15 is positive 15. So our vector picture, we have negative 27. Positive 15 goes the other direction, but it's shorter. So we stop short of the 0, so we stay on the negative side. The difference, they go opposite directions, so we're looking at the difference between the lengths, which is 12, negative 12. Multiplying is a little bit simpler. We saw that if we have positive 5 times 3, that's just repeated addition. 3 5s added together. 5 plus 5 plus 5 is 15. Well, that isn't a big stretch then for negative 5 times 3 is just 3 negative 5s added together, which gives us a negative 15. The one that we have to do a little bit more work on is this one. 5 times a negative 3. We cannot take 5 and add it together negative 3 times. That doesn't make any sense. But what we can do is in multiplication, we can change the order of the numbers, what we call commutative, to do negative 3 times 5. Now that's saying take negative 3 and add 5 of those together. Negative 3, plus negative 3, plus negative 3, plus negative 3, which is negative 15. Now, most of you, like I said, have had algebra, even pre-algebra, you probably would have seen this. You've learned that when you multiply a negative times a positive, you get a negative, then just multiply the numbers. 3 times 5 is 15. Or the other side, if you had multiply a positive times a negative, again, you multiply the numbers. 5 times 3 is 15, which is negative. The other one, the final one, negative 5 times negative 3, you've all been taught, well, negative times a negative is a positive. That has to be positive 15. But the question comes down to why. This is saying take the negative 5 and add it together negative 3 times. We can't do something a negative number of times. Even if we switch the order, we commute it, that would be saying take negative 3 and add negative 5 of them together. That doesn't make sense either. The definition of multiplication does not work when we're multiplying two negatives. So how do we end up with the idea that it ends up being a positive 15? Well, this actually happens more often in math than you would think. And what it comes down to is patterns. When we have something where the basic definition breaks down, we look at similar problems where the definition works, and we try to establish a pattern. For example, we know that negative 5 times 3 is a negative 15. So to establish a pattern, we're going to keep part of the original problem the same. We're going to keep the negative 5 times the same. And then we're going to change one piece and see how it affects the answer. Here, what we're going to do is we're going to reduce this number by 1. This will be negative 5 times 2. Negative 5 times 2 is negative 10. And what happened over here was the result went from negative 15 up to negative 10. It increased by 5. Let's keep that going. Negative 5 times, reducing that by 1 again, would be 1. Negative 5 times 1 is negative 5. Again, the answer increased by 5. So we've established a pattern here. Negative 5 times 0, we reduce that by 1 again, equals 0. This went up by 5 again. So now if we keep going into the ones that are not defined, negative 5 times, well, 0 minus 1 is a negative 1. Again, we can't do a negative times a negative with our basic definition, but we can continue the pattern. We add another 5, 0 plus 5 is 5. Negative 5 times negative 2, again, we increase it by 5 to get 10. Negative 5 times negative 3, increase it by 5 to get 15. So the long answer to the simple question was the reason why you multiply two negatives and get a positive is because it continues this pattern. So anyway, I understand that you guys have worked with integers before. I'm not going to pound it into you. I just wanted you to see, first of all, I wanted to make sure we reviewed the subtraction, but I wanted you to see why those rules that you memorized actually apply. The last thing we want to do is we want to look at one more set of inverse operations. We have seen addition and subtraction. And they're called inverse operations because in math, whenever we do something, we have to have the ability to go back, to undo it and get back to where we started. If we select random numbers like 4 plus 7 is 11. If I wanted to get back to the 4, I'd do 11 minus 7, get back to 4. Adding 7 and subtracting 7 are inverses. They reverse each other. Or the other way around. If I started with 7 and I subtracted 4, I'd get 3. If I want to get back to the 7, I take my 3 and I add 4. Here I did it the opposite order. I subtracted first and then added. But again, they reverse each other. They get us back to where we started. And multiplication and division do the same thing. Let's start with 12 times 3 is 36. If I want to get back to 12, I take my 36 and I divide by 3 to get to 12. Multiplying by 3 and then dividing by 3 cancel each other out. Put us back to where we started. We're going to start it out with the 12 and I divide by 3 to get 4. If I want to get back to the 12, I do 4 times 3 to get 12. Dividing and then multiplying by the same number again, put us back to where we started. There are actually several other pairs of these inverse operations. There's logarithms and exponentials, which we won't get into in this. Trig functions and their inverse. The one that we will mention is exponents. Exponents have two parts. First is this one. 8 to the third power is how that's pronounced. Literally means 8 times 8 times 8, or 512. Well, this is an exponent. That exponent has two parts. The 8, which is the number being acted upon, is called the base of that exponent. The 3 is called the power, telling us how many times the base is repeated. Well, if we can have a power, we need to have an opposite or an inverse of that. The inverse would be a root. To indicate what power the root is reversing, we put an index here. That is called the index of the root. And if I ask to do the third root of 512, that is asking what number to the third power is 512. Well, we just saw that up here. It's the 8. This is the base of the root. If I took 7 squared, of course we all know that's 49. To reverse that, we use the square root. Now notice there is no number, no index written in here. We assume that to be the 2 that we're reversing the squared. The square root of 49 is 7. We don't have any more time left, so I'm not going to get into how the powers and roots affect the negatives, but we'll let you guys look that over. Your first homework assignment is out of your book, page 7 and 8, 1 through 59 in the odds. Now I realize that is 30 problems. Remember, I do not collect your homework and grade it. The homework is here for you to practice and learn. So I always put the little caveat out there. If you do the first couple problems and they're extremely easy, feel free to skip ahead to some of the more difficult ones. Make sure you at least do the word problems, because the word problems are going to be very similar to what appears on your test. And also, just so you know, like I said, test 1 is on February 8th. On that test, I shouldn't say no calculator. I should say you have to show your calculation. You can use your calculator, but you have to show the calculation. You have to show setting up the problem, borrowing if you're subtracting, going through setting up the long multiplication or division and all that. With that, that is our time right there. So you guys have a great day, and we'll see you all on Friday.